All right, hello and welcome. Today, we're basically becoming cosmic detectives. We're heading out about 3,700 light years to the constellation Vulpecula to investigate a very old, very weird cosmic mystery, a faint, rhythmic signal from a very special star. So what's the big question here? It's this: what can a star's unique rhythm, its own cosmic heartbeat, actually tell us about what it is? Well, we're about to find out that sometimes the biggest secrets are hiding in the quietest whispers from space. Now, our target is a pulsar. Just so we're all on the same page, the easiest way to think of a pulsar is as a cosmic lighthouse. It's the super dense, spinning corpse of a star that's gone supernova. And as it spins, it shoots out these beams of radiation. If we're in the path of that beam, we see a pulse. Simple, right? Well, not so fast. Okay, so time to meet our main suspect. And this isn't just any old pulsar. This star has a long history of sending, well, mixed signals, and it's had astronomers scratching their heads for decades. Its name is PSR B2016+28. Now, not only is it one of the brightest radio pulsars we can see from the Northern Hemisphere, but this star is famous. It's one of only 14 pulsars whose location was engraved on the golden plaques on the Pioneer and Voyager spacecraft. You know, the cosmic maps meant for any intelligent life out there. So yeah, the fact that this famous star was so hard to figure out made its mystery even more frustrating. And here is the heart of that old mystery. For years, the evidence was completely contradictory. Some studies looked at the data and said, yep, it's one single wide lighthouse beam. But then other studies came along and said, nope, you're wrong. It's actually two separate beams. So which was it? For a long time, the case just went cold. Our instruments just weren't good enough to tell for sure. But you know how these cold cases get solved, right? A new piece of tech comes along and just blows everything wide open. It lets you see things that were totally invisible before. In our story, that breakthrough is a telescope that is just absolutely massive. Meet the 500-meter aperture spherical radio telescope, or as everyone calls it, FAST. And yeah, that dish is a staggering 500 meters across. It's the biggest of its kind on the planet. It's pretty much the ultimate magnifying glass for listening to the universe. Because FAST is so incredibly sensitive, it could finally gather the super detailed, high-quality evidence that scientists needed to reopen this cold case and finally, hopefully, settle the debate once and for all. So, the first order of business for the FAST telescope was tackling that big, fundamental question: one beam or two? The answer to this was going to be the first major clue to cracking this whole thing open. And boom, the verdict came in and it was crystal clear. The data from FAST proved, without a doubt, that the signal comes from a single, hollow cone of radiation. So, case closed on that mystery. We were looking at one lighthouse beam the whole time. But you know how these things go. Solving one mystery just opened the door to a new one, and this one was even stranger. With the shape of the beam figured out, scientists could now zoom way in on the tiny details of the signal. And what they found in there, well, it looked like ghostly footprints, appearing and disappearing inside the main pulse. Okay, to really get what they found, you have to understand this one key difference. There's the mean pulse. That's the average signal, the steady flash of the lighthouse you see over time. But FAST is so powerful, it can see the single pulses, the individual split-second flickers and sparks inside each flash. And that's where the real clues were hiding. So here's what they saw. Inside the main flash, there were these fainter little sub-pulses. But they weren't just sitting still. They were drifting. They moved across the pulse in this chaotic, totally irregular pattern. It was like watching sparks dance randomly inside a flame. This erratic movement was a huge clue that whatever was creating this beam was not a nice, orderly process. And this is where the investigation gets really good. While they were studying this weird drift, scientists stumbled onto a totally bizarre contradiction. A piece of evidence so unexpected, it became the smoking gun that cracked the entire case. And you know how they found it? By doing something that sounds super simple. They just changed the channel. They looked at the pulsar at different radio frequencies, tuning from low to high, and they expected everything to change in a predictable way. It did not. Okay, so check this out, because this is the whole thing right here. As they tuned up the frequency, the overall beam, the average lighthouse flash, it shrank by about 20%. That's kind of what they expected. But the little drifting sparks inside, they barely shrank at all, only about 1.5%. How is that even possible? How can the whole beam get narrower, but the sparks inside stay pretty much the same size? It made no sense. This crazy disparity was the key. It pointed directly to a very specific theory about how pulsars work, this idea of a vacuum gap. It's this empty space right above the star's surface where these massive electric fields can literally create sparks of plasma out of nothing. So this wasn't just a weird observation anymore. It was a clue to the fundamental physics of the star itself. So we have all the pieces on the table now. A single beam, irregular sparks drifting around inside it, and this totally bizarre size contradiction. Let's put it all together and see what it tells us about the actual star. Okay, follow the logic here. 1, we see these weird, irregular sparks. 2, the sparks don't shrink like the rest of the beam. 3, that means they must be created really close to the star's surface, inside that vacuum gap. So what would make these sparks drift so chaotically? The best explanation is that the surface of the star isn't smooth at all. The drift is caused by a rough, uneven stellar landscape, kind of like lightning striking randomly over a rugged mountain range. So let's close the case file. The big question, 1 beam or 2? Solved. It's a single cone. Why was the signal so irregular? Because of drifting sparks of plasma. And what caused that chaotic drift? A rough, uneven surface on the star itself. It's amazing. From a faint, confusing pulse, we have actually figured out the very texture of a star thousands of light years from Earth. And that really just leaves you thinking, doesn't it? This whole investigation didn't just solve a puzzle about one star. It proved that if we can build tools that listen carefully enough, we can map out features on distant worlds we never, ever thought we could see. It makes you wonder, if the secret to this pulsar's rhythm was a rough surface, what other mind-blowing cosmic secrets are just out there waiting for us to find the right way to listen?